What is the age of our universe? This question has puzzled scientists for centuries. Although it seemed like a simple question, over time it has become clear that finding this answer is not so easy. Today, this question remains a matter of controversy, due to new studies that continually challenge our understanding of the ancient, myriad galaxies that make up our universe. A week ago, a groundbreaking study based on data from the James Webb Space Telescope called into question the widely held notion that our universe is approximately 13.8 billion years old. In this study, it is suggested that the universe could be twice as old, breaking with the cosmological model and solving the enigmatic and complex problem of the first galaxies. But really, is this possible? Join us on this trip, because we are going to immerse ourselves in the immensity of the cosmos to analyze this discovery. If you are interested in keeping up to date on news from the universe and its surroundings, please subscribe to our channel and be sure to like this video. Importantly, one of the most revealing facts about the universe is that we know its age, 13.8 billion years. However, this figure is being questioned and reassessed based on exciting new research. If we were to go back in time, we would discover that the early universe was very different from how we know it now. The stars and galaxies we observe today arose through gravitational mergers of objects that consisted of younger, more pristine stars. In those initial moments, there were no stars or galaxies. If we continue to look into the past, we would reach the moment of the Big Bang, which marks the beginning of the universe as we know it today. Today, astronomers and astrophysicists studying the early universe say they have estimated its age with an uncertainty of less than 1%, a remarkable achievement that represents the discovery of the universe's birthday. To measure the age of the universe, there are two methods compatible with this figure. The first is to trace the history of the universe, a powerful way to estimate its age. This method is based on the discovery of the expansion of the universe in the 1920s. In physics, if you know the equations that govern the system and you know how it evolves over time, you can go back in the past or forward into the future, as long as the laws of physics and the content of the system do not change. In the field of astrophysics and cosmology, the laws governing the expansion of the universe require solving the theory of general relativity for a universe that is, on average, filled with equal amounts of stuff everywhere and in all directions. We call this a homogeneous universe. It is the same everywhere and isotropic, since it is the same in all directions. The consequences of this solution are known as the Friedmann equations, after Alexander Friedmann, who first derived them 99 years ago, in 1922. These equations tell us that a universe full of things must expand or contract in a particular way. The rate of expansion or contraction changes over time and depends solely on two main factors. First, the speed of expansion at any point in the present. Second, what kind of content does the universe have at that specific point? In the early days of cosmology, they used to joke that cosmology was the search for two numbers, implying that if we could measure the rate of expansion and how it changes over time, we would have all the information we need. Currently, we know those two numbers, the Hubble parameter, which represents the current expansion rate of the universe, and the deceleration parameter, which is negative. This means that the universe is not slowing down as previously thought, but is instead accelerating its expansion. If we could accurately determine the expansion rate of the universe, we would be able to know in detail the composition of the universe. That is, we could know about normal matter, dark matter, radiation, neutrinos, dark energy, and other components that are present. We could also go back in time to the initial moments of the Big Bang, when the universe was very hot, dense, and occupied a small volume. The amount of time we take to go back to that point gives us the age of the universe. The study was published July 7 in the monthly notices of the Royal Astronomical Society. And this seems to confirm that previous estimates of the age of the universe were significantly wrong. This new study addresses what is called the riddle of the first galaxies, which has long puzzled scientists. According to this study, some galaxies that were thought to have existed shortly after the Big Bang actually appear to be much older than previously thought. Observations made with the James Webb Space Telescope showed that galaxies and stars, such as Methuselah, appeared to have a level of mass maturity normally associated with billions of years of evolution. This is surprising, considering that these galaxies were widely believed to have formed hundreds of millions of years after the Big Bang. An associate professor of physics at the University of Ottawa suggests that these puzzling observations can be explained because our universe is actually much older than previously thought. This professor's study presents a new model that extends the formation time of galaxies by several billion years, giving the universe an age of 26.7 billion years, double what is generally accepted. This model incorporates the tired whiskey light theory, which suggests that the observed redshift in light from distant galaxies is due to a gradual loss of energy over large cosmic distances. According to Swift's theory of tired light, light becomes weaker or tired as it travels great distances through the cosmos. This idea contrasts with currently established theory, which holds that the redshift observed in objects such as galaxies is mainly due to their receding from us as a result of the expansion of the universe in all directions. The tired light theory has generated significant controversy within the scientific community. Astronomers discussed whether the loss of light energy over cosmic distances would not only cause a redshift, but also a decrease in light intensity and brightness. Critics argued that if this were true, distant objects could appear much dimmer than is actually observed. Furthermore, this theory proposed by Whiskey in the mid-20th century conflicted with the discovery of cosmic microwave background radiation. It is a uniform radiation present throughout the sky and represents the residual energy of the Big Bang. This radiation provided strong evidence in favor of the expanding universe theory. Although Whiskey's theory was initially conflicted by observations, a new perspective is proposed that allows the light theory to coexist with the expanding universe model. According to this new interpretation, the redshift phenomenon can be seen as a hybrid phenomenon that combines both the expansion of the universe and the gradual loss of energy of light during its cosmic journey. This new interpretation offers a credible explanation for the first observations of galaxies. In addition, the tired light theory is considered and the concept of blocking constants is also introduced, an idea proposed by the physicist Paul Dirac. These blocking constants are fundamental physical parameters that cause the interactions between particles, and it is suggested that they could have varied with time. By taking into account the evolution of these blocking constants, the new proposed model extends the time frame for the formation of the first galaxies observed through the James Webb Telescope. Instead of just a few 100 million years, this new time frame allows several billion years of cosmic evolution to be covered, providing a satisfactory explanation for the development and mass of these ancient galaxies. This model also challenges the traditional interpretation of the cosmological constant, which represents the dark energy responsible for the accelerating expansion of the universe. Instead, a modified constant is proposed that takes into account the evolution of the containment constants. This modification in the cosmological model may help solve the perplexing puzzle of the small size of galaxies observed in the early universe and provide a more accurate picture of cosmic evolution. And you, do you think? Do you think we've been wrong all this time? Let us know in the comment box. If you like the video, remember to hit the like button and subscribe to the channel so you don't miss more content like this.